Okay, our last lesson of probability is dependent and independent events. So first we're going to define those two things. We're going to start with independent because it's a little bit easier. Independent events are two or more events where the outcome of one does not impact the outcome of the other. Okay, so for an example, flipping a coin more than once, right? Because the outcome of the first one isn't going to impact the outcome of the second one at all. Okay, spinning a spinner and rolling a die. Okay, so again, the outcome of this does not impact the outcome of this. Okay, then the last one would be drawing a card. So if you have like a deck of cards and then you put it back and then drawing another card. So it's not going to impact that second one because you've put back the card that you took, so you could get it again theoretically. Okay, the flip side of that is dependent events. So this is kind of how it sounds. They depend on each other. So two or more events where the outcome of one impacts the outcome of the other. Okay, so one example would be drawing a card, then drawing another one without replacing the first. Because let's say you're talking about drawing red cards or black cards, something like that. If you draw a red card the first time, the probability that you draw a black card the second time actually goes up because there's less red cards in the deck. Okay, another example of this would be picking letters from a Scrabble big, right? So if you have the big of letters and you pick one, you're not putting it back, you're going to use it, right? So what's left in there depends on what's already been picked. Okay, so something to think about is the words without replacing are generally a clue that the events are dependent. There's a few other ways that we can look at that, and that'll come up in the lesson. So if we're talking about the probability of independent events, you guys have actually been doing this in previous math courses. So you would have done this in like grade 8 and grade 9. So when events are independent, use the following formula to determine the probability of both of them occurring. So the probability of A intersect B. So remember, this thing means and. So A and B have to happen is the probability of A and the probability of B multiplied together. Okay, so if we want to calculate the probability of rolling a number greater than 6 or greater than 3 on a 6-sided die and flipping a coin and getting heads, okay, we're going to say the probability of A. Okay, first thing that we should look at here is that these are independent, right? This is the example, but I just want to get into a habit of let's write out whether or not we are looking at dependent or independent. So the probability of A, okay, we'll call A in this one is a number greater than 3 and B is getting heads. Okay, so the probability of A, we can either get 4, 5, or 6, so 3 out of 6 options. Reduce that to 1/2. The probability of B is getting heads, so 1/2. So the probability of A and B is going to be 1/2 times 1/2, so 1/4. Okay, so that's how we do it if we have independent events. The next thing that we're going to look at is the probability of dependent events. So in this case, the probability of each event needs to be calculated, but this time we need to consider the probability of B occurring if A has already occurred. So this time we're going to do the probability of A and B as the probability of A. That's the first event. So this time order really matters. And then this is the probability of B given A. So this like vertical line here means given. So let's actually make a little note. So this is the probability of B, I don't know what that was, B given A. So if A has already happened, what is the probability of B? So we're going to look at that, okay? So the numbers 1 to 10 are on cards in a pile. What's the probability of drawing a 4, then an 8 if the cards are not replaced? Okay, so basically you're going to pull a card, and then you're going to keep it, and then you're going to pull another card. So we want to know 4, then 8 in that order, okay? So we're going to call the probability of drawing a 4 event A, probability of pulling a 8 event B, and again, these ones are dependent, okay? So the probability of A is 1 card out of the 10 is a 4. Then we want to look at the probability of B given A. So if the 4 was pulled, great. Now we only have 9 cards left, right? Because that 1 card has already been pulled. And so then we have a 1 in 9 shot. So now when we do PA intersect B, we're going to have 1/10 times 1/9. So there's a 1 in 90 shot that you pull a 4 and then an 8 if you don't replace them. Okay. In the cases, so in cases where 2 different events can happen in a variety of orders, we need to calculate the probability of each of them and then add them together. Okay, so we kind of look at this as 2 different scenarios. So we're going to go over this in the following examples. So these 2 examples are similar but different because of that order piece. So I'm going to roll a fair 6-sided die twice. What's the probability that the first roll shows a 5 and the second roll shows a 6? So it's very specific that we want a 5 on the first roll and a 6 on the second roll. Okay, so if we want both of those, again, so probability of a 5, we're going to call that event A. Probability of a 6 on the second roll, we're going to call that event B. Okay, and then the first thing that we want to do is figure out whether it's independent or dependent. So this one's independent. Okay, so we're going to figure out the probability of getting a 5 on the first roll. So we know that that is 1/6. And then the probability of getting a 6 on the second roll, that's 1/6. So then P of A and B together is going to be 1/6 times 1/6, so 1/36. Okay, so this next example is a little bit different because we're going to have 2 different scenarios. So I roll 2 fair 6-sided dice. What's the probability that a 5 and a 6 are shown? Okay, so the reality of rolling 2 dice is one usually lands before the other. So we're going to think of that when we're doing this. So there's kind of 2 scenarios. Oh, first, this is independent, right? The roll of one isn't going to impact the other. So that's the first thing that we want to do. Then we want to think about there's 2 scenarios here. Okay, so I get a 6, then a 5, or a 5, then a 6, right? Because if I roll a 6, then I'm looking for a 5. If I roll a 5 first, then I'm looking for a 6. Okay, so I'm going to call event A rolling a 5 and event B rolling a 6. And what this is going to do here is we're going to have to do the probability for each of these scenarios. So the probability of getting an A and a B is going to be 2 different situations that we can have here. We can do the probability of getting an A, so a 5 with the first dice, times the probability of getting a B, so a 6 with the second die. Or, right, so we're going to add them together because these are 2 different scenarios. There's going to be a probability of each, and then we're going to add them. So we can do the probability of getting an A on the second die, so a 5, times the probability of getting a B, so a 6 on the first die. Okay, so if this is die 1 and die 2, die 1 and die 2, this encompasses these two different scenarios that we can have here, okay? So the probability of an A, so a 5 on die 1 is 1/6, and a B, so a 6 on die 2 is also 1/6. And then A, so 5 on die 2 is 1/6. And then a B, so 6 on die 1 is 1/6. So we have 1 over 36 plus 1 over 36. We add those together. We get 2 over 36. We can reduce that to 1 over 18. Okay, one of the ways that we can look at this is, I'm going to draw this. So if I have my first die, I can either have a 1, 2, 3, 4, 5, or 6. My second die, I can have a 1, 2, 3, 4, 5, or 6, right? So I've basically just drawn out the combo. So I could have a 1 and a 1, a 2 and a 1, a 3 and a 1, a 4 and a 1, a 5 and a 1, a 6 and a 1, okay? But I could also get, so if I was thinking about this 2 and 1, I could get a 1 and then a 2 instead of a 2 and then a 1, right? So see how there's two different options for 1 and 2? Same deal here. We can have a 5 and a 6 or a 6 and a 5, okay? Because this is a 6 by 6 grid, right? 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6. This is 36 different options. So we have 2 of those 36 different options giving us a 5 and a 6, okay? Because the order doesn't actually matter. It didn't say the first die has to be this, second die has to be this. It just wants both, and so we can either have first, second, or first, second. Okay, so that 2 out of 36 is what we solved for. So that's why it's really important to have that two different scenario method. Okay. So then, a couple more examples. So if we have the set of cards below, so we have, I don't know what these cards are, but we have 4 R cards, 3 A cards, 5 D cards, and 4 W cards, so 16 total. We're going to draw 2 cards one at a time, replacing the first one before the second one is drawn. We want to know the probability of getting an R and a D. Okay, so an R and a D, it could either be, we're going to have 2 scenarios again. We could do R, then D, and then D, then R. Okay, so because we're just looking for R and D, not R then D, right? We have to do 2 different scenarios, get the probability for each of them, and then add them together. It kind of gives us 2 shots at getting this thing. So, if we're replacing the first one before the second one is drawn, this again means this is independent, right? Because then whatever card you picked the first time is back already and you could pick it again, right? It's not gone from the pile. The number of options remains the same. So we're going to do, this is going to be equal to the probability of picking an R with your first one times the probability of picking a D with your second one, plus the probability of picking a D with your first one, times the probability of picking an R with your second one. So we're going to actually do those as fractions. So we've got the probability of R, we've got 4 out of 16. Probability of D, we've got 5 out of 16. Plus the probability of D, so that 5 out of 16 again, times 4 over 16, that probability of R. Okay, so when we simplify this, so that I didn't have to get my calculator out, I reduced these ones to 1 over 4, and then 1 over 4, because then I just have 5 over 64, plus another 5 over 64, that's 10 over 64. So when I reduce those, I can divide them both by 2. I get 5 over 32. Okay. This second example here, we draw 2 cards one at a time without replacing. So this means that these are dependent because the second probability is going to depend on what you pull the first time. So we're going to do the probability of R and W prime. Okay, so in this case, because it's dependent, this order matters this time, right? Because we're going to do R first and then we want W complement. Sorry, I called it prime. That's a calculus thing. W complement. Okay, so the probability, and if you like the intersect symbol better than and, that is totally cool with me, is going to be the probability of R times the probability of W complement given R. So if you get R in the first one, you're going to have to do, then you're going to have a different probability for W prime. So the probability of R is 4/16. And then the probability of W given R. So let's assume we pulled an R the first time. Now we only have 15 cards left. Okay, so instead of being out of 16, this is going to be out of 15. And if it's W complement, we're looking for anything other than a W. Okay, so it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 options because one R is gone. The other 11 that are not the W are the things that we want. Okay, so then we want to, again, I'm going to cancel these, so 1/4. So then I have 1 times 11 on the top, 4 times 15, which is 60 on the bottom. And so I have 11 out of 60. That is not going to reduce because 11 is a prime number. Okay, so that would be our this would be the probability of R and W complement, the opposite of W, anything other than a W, if we don't put that first one back. Okay, last couple examples. If we have a coin flipped 3 times, what's the probability of all 3 being heads? These guys are independent. Right, so the probability of heads and heads and heads is going to be the probability of heads times the probability of heads times the probability of heads. Okay, so that's going to be 1/2 times 1/2 times 1/2. So we get 1/8. If we do this next example, a basket contains 5 apples and 7 peaches, so 12 total. You randomly select one piece of fruit and eat it. If it's eaten, that means it's gone. We cannot, it doesn't go back in, right? So this is going to be a dependent situation, okay? Then you randomly select another piece of fruit, find the probability that the first piece of fruit is an apple, okay? So that's going to be event A, and the second piece of fruit is a peach, event B. Okay, so we want the probability of A and B. That's going to be the probability of A times the probability of B given A on our first shot. Okay, so the probability of A, there's 5 apples out of 12 possible. And then remember, when you eat one of those 12 pieces of fruit, now you only have 11, and you're looking for one of the 7 peaches. So that's going to be 35 on the top, and then 12 times 11 is 100 and, what even is that? It's 121 plus another 11, so 132, okay? I don't think that that is going to simplify. You can check on your calculator. I don't have mine. Okay, last example, we have Danny has a blue, red, and a green tie. He also has a blue tie and a blue and a green shirt. He chooses a tie and a shirt randomly. Find the probability that he's wearing all one color. Okay, so it doesn't really matter order here. What we're looking for, and this is independent, right? Because if he randomly chooses both, independent, I can't spell this word. If he randomly chooses both, they're not going to influence each other, okay? So I'm going to call event S a shirt and event T a tie. Okay, so the probability of a shirt and a tie matching is going to have two different scenarios. Either he can match with blue because he has a blue tie and a blue shirt, or he can match with green. So we're going to figure out the probability that he gets blue and the probability that he gets green and add those together. So the probability of the shirt and the tie matching is the probability of the shirt being blue times the probability of the tie being blue plus the probability of the shirt being green times the probability of the tie being green. Okay, so he's got 2 options for shirts and 3 options for ties. So the probability of the blue shirt is 1/2, right? 1 out of 2. Probability of the blue tie is 1/3. Okay. If we want to do the probability of the shirt being green, again, that's 1/2 because it's 1 out of the 2 options. And then the tie being green is 1 out of the 3 options. So you get 1/6 plus 1/6. So 2/6. So 1/3. Okay. A nice easy way that we can check this, so similar to what I had set up previously for the dice rolling, is we can look at, okay, so here's ties, here's shirts, right? Ties he has blue, red, and green. Shirts he just has blue and green. Okay, so if you kind of make a little chart for yourself here, if he picks blue tie and blue shirt, that's blue, blue. If he takes blue tie and green shirt, that's blue, green. Red and blue, red and green, green and blue, green and green. So see how these 2 are the 2 out of 6 where we had those 2 matching colors, and that's going to reduce to 1/3. So if it's a small number like this, this is a really good way to check your logic, okay? If you have, oh, I forgot to put the snap stuff. You should basically be doing lesson 3. I think, no, it'll be on yours. It's just not here. It'll be on yours though. So if you have any questions, let me know. Okay.